When we talked about the 4 different quantum numbers, the angular momentum quantum numbers, or L, talks about how that describes the shape of the orbital. So what we're going to look at is 3 that we would see most often, and we would talk about the different features of these orbitals. We're going to start with the simplest orbital, which is the s orbital. That's an orbital that has an angular momentum quantum number L equals to 0, and the s is an orbital that has a spherical shape, and a lot of times people would think that's the reason why the letter S comes about, but the letter S actually has to do with the actual shape of the lines in the spectroscopic measurements of the electrons in these different orbitals. The shape of the S orbital is shown here in 3 dimensions, and this is just a cutaway form of it, but you can see that it's a sphere. Like this picture here shows the 1s, 2s, and 3s orbital. See, the main difference is of course the size of the orbitals. Remember that first number 1, 2, and 3 represents the principal quantum number, which corresponds to the size of the orbital and the energy of the electrons in it. So what we see here is just a bigger size orbitals when you go from 1 to 3s. And then the other thing we see is there's this portion that's colored white here once we have the 2s orbital, and then when we have the 3s orbital, we have 2 parts of these that are colored white. If we actually plot this out in the total probability distribution, again something that we discussed in a prior video, you will see that those white regions actually corresponds to the nodes in the wave function of that specific s orbital. So the reason why this one has no white part in the structure of the orbital is because there's no node there. And then with this one you have one node right there, and that node corresponds to that white space. And then here you have 2 nodes, so that corresponds to those 2 white spaces. Remember that the nodes are areas where the amplitude of the wave function is equal to 0. Of course, if we look at it from the Born interpretation of the wave function, which is corresponding to the probability of finding the electron, if you have an amplitude of 0, that means that there is 0 probability of finding electrons there. So electrons cannot be found in those specific location in the s orbital. With the p orbital, we have the angular momentum quantum number equal to 1, and the shape of it is different. It actually looks like 2 lobes. So with the s orbital, you can think of it as having just 1 lobe. With the p orbital, you have 2 lobes. Now, the way the p orbitals are drawn is always with 2 different colors, or sometimes you might see the same color if it's a black and white picture, but then it will have a plus on one side and a minus on the other side. The reason why they are drawn that way is to indicate that the phase of one side of the p orbital is different than the phase of the other side of the p orbital. Now, what do I mean by phase? Going back to our original discussion about waves, some waves are above that 0 displacement line, and some waves have amplitude below that 0 displacement line. So when we have it above the 0 line, we call it positive phase, and when we have it below, we call it negative phase. And that's the reason why the p orbitals have those 2 colors, because they're of opposite phases. The importance has to do later on with bonding. So depending on whether the bonding occurs between lobes that have the same phases or opposite phases, you're actually going to get different types of chemical bonds. The p orbital, a lot of times you'll see it drawn more like a figure 8, but it actually has a node right in between the origin there, which is the position of the nucleus. So there is a node on all of these p orbitals. Now, why are there 3 different p orbitals? If you recall, when L is equal to 1, the value of m sub L can be -1, 0, and +1, right? M sub L, remember, represents the orientation of these p orbital. When you look at these 3 different p orbitals here, you notice that they're all just aligned on the coordinate axis themselves. So because the coordinate axes are perpendicular, or the word that we use if it's 3-dimensional is orthogonal to each other, then the p orbitals are also orthogonal to each other. And we call them px, py, pz based on the axis that they are lined up with. The d orbital is the next level. In this case, your L value is equal to 2. And of course, if your L value is 2, then your m sub L value is going to be -2, -1, 0, 1, and 2, which means that there are 5 different d orbitals that are possible. So the 5 different d orbitals are shown here, and they all have 4 lobes with the exception of that last one, and that shape is called a torus shape in math. They have the different phases as well, so positive and negative phases, and they have these names that are a little bit less easy to remember. So dxy here, the lobes are aligned on the diagonal between the x and the y. The xz is on the diagonal between the x and the z, and so on. The x squared, y squared, that's aligned on the x and y. and then the torus, of course, is the one that's lined up on the z-axis. Might be a little hard to remember these, and typically in my classes I don't really expect the students to remember the actual names of these, just to know that there's 5 different orbitals there. You can go to higher level orbitals. F is the next one over, and that's going to have 7 different orbitals. That's the one that you'll see often enough to need to know. So we're going to now get into a very important topic in quantum mechanics, which is the understanding of the energy of the electrons in orbitals. Why is this an important topic? Reason is because all the reactions that occur in chemistry is really a function of how reactive the atoms or the ions or the species that contain the electrons. So the energy of the electrons, whether the electrons is stable or unstable, is going to determine the chemical reactivity of the species that the electrons are located in. What we're going to do here is look at 2 different systems that contain electrons in them. First one is the one electron system, and then the next one is the one that's a lot more useful, which is the multi-electron or polyelectronic system. It's not quite possible to talk in depth about the multi-electron system in general chemistry, but we would use a lot of the ideas developed in the one electron system to help us understand the multi-electron or the polyelectronic system. The one electron system is really the system that we had discussed before in the Bohr model. So if you recall, the Bohr model was very well developed to address the observations in the one electron system, specifically the hydrogen atom. But later on, it was discovered that you can use that same equation that Bohr proposed, which is this equation highlighted in yellow, to calculate the energy of electrons in other one electron systems. So for example, the lithium 2+ ion. Recall that the equation itself has the following components: RH, which is the Rydberg constant, Z is the number of protons in that system, and then N is the principal quantum number, or is the Bohr orbit if you're looking at it from the Bohr model. You can use that equation to calculate the energy of that electron. Notice that with this equation, there is no other component of the other quantum numbers except for N, which is the principal quantum number. As a result, if you go to N equals 2, you can have 2 different orbitals. You can have the 2s orbital and then the 2p orbitals. But because in the one electron system, the energy doesn't really depend on the shape of those orbitals, just where the level of the orbital is. The 2s and the 2p orbitals, whether the electron is in this one or that one, they're going to have exactly the same energy. Same applies to when you go to the 3rd level, where you have the 3s, the 3p, or the 3d orbital. Whether your electron is located in any one of them, they're all going to have the same energy. When we have orbitals that all have the same energy, we call them degenerate orbitals. So the diagram for the energy of a one electron system looks like this. So you can calculate the energy for a given system like the hydrogen atom or the lithium 2+ ion. The RH and the Z won't change. The N is what's going to change. So for N equals 1, it's going to have a very negative value. And then when you go to N equals 2, it's going to be a quarter of the value of the N equals 1. And so what that means is that the N equals 1 is going to be the most negative, which just means it's the lowest in energy. And then the N equals 2 is then going to be 1/4 of the number that you have for the N equals 1. So it jumps up very quickly to this level. And then when you get N equals 3, if you plug in 3 here, 3 squared is 9. So then the value of energy is 1/9 of the N equals 1 value. So it's even higher. So what you can see immediately is that energy goes up as you go further away from the nucleus, which is what we had said before. Not only that, you also see that the difference between these 2 energy levels and these 2 energy levels is much smaller here. As you go up higher and higher and higher, the difference between successive energy levels becomes smaller and smaller and smaller, and this has important consequence in the polyelectronic system. This question asked us about comparing stability for a one electron system. A one electron system can be calculated using the Bohr equation, which is just E sub n equals to negative RH times z squared over n squared, where z represents the number of protons, n represents the shell number or the principal quantum number. For comparing stability, what we have to do is calculate the energy and find the one that is lowest, and that would be the most stable species. So the ground state of hydrogen atom, ground state, remember, means n equals 1 for the hydrogen atom. So what we're trying to do is calculate E when n is equal to 1, which means we're going to calculate negative RH. The Z, or the number of protons for hydrogen atom, is 1, so it's 1 squared over 1 squared again, because the n is equal to 1 in this case. So if you calculate that out, all you get is just negative RH. And I didn't want to write the number here because all we need is just comparing the magnitude of your answers. If you go to the first excited state of helium plus, here we're talking about n equals 2, because if you recall the Bohr model, you have the nucleus, you have n equals 1, and then that's your ground state, and then you have n equals 2, and that's your first excited state. So to calculate it, we would take negative RH. Since it's helium, the Z, or the number of protons, is 2, so it's going to be 2 squared. And then since it's first excited state, the n is also 2, so it's 2 squared again. So it ends up canceling, giving you negative RH. The first two species actually have the same stability. Let's take a look at the third species. The first excited state of beryllium 3+. First excited state means n equals 2. Beryllium has a Z of 4. Number of protons is 4. So 4 squared over 2 squared, and that gives us negative 4 RH. So this number is much more negative than the other two, which means that if I'm drawing an energy diagram, if negative RH is here, then negative 4 RH must be down here, right? So that one is a lot more stable because it's much lower in energy. So that last one is the most stable species.